very happy that Ken is with us to talk about the importance of open-endedness in AI and machine learning. So Ken, thank you very much for joining us and for talking about your interesting work. So it's over to you.
Thank you. It's great to kind of be here, and I appreciate you guys giving me this chance. And I'm going to talk about why I think open-endedness is important. And forgive me if I haven't been here for the earlier session, so it's possible I may say something slightly redundant. So this is kind of how I frame the question that leads me to open-endedness. Because really thinking about it from the perspective of AI, and here's actually I without the A, and it's just really fascinating to me, and always has been, how something could produce something like this that was not actually trying to create it explicitly. How could it be that there was a process that created something like our brain, but it wasn't actually set up to create a brain? And connected to that, how does astronomical complexity, like the 100 trillion connections inside of this thing, arise from a process that's basically completely unguided? And that's evolution. And we should care about this kind of thing, because we might have to ignite this kind of a process if we want to achieve something like AGI or even human level AI, and many other things too. May require a process like this. And so it's also true that it might be easier to formalize a process, like a process that produces something like this, rather than to formalize the brain itself. And I think this is a kind of a perennial debate, like, should we build things that build brains, or should we just build brains? And sort of the learning angle, the machine learning angle, is sort of like, let's build something that will at least in part build the final intelligent entity, rather than trying to do it all by hand or through our own intelligence. And so it may be that we need some kind of process like the one that created our own brain in order to get something like a brain. And so sometimes I think of this process, and we talk about what is this process. I mean, we know this is called evolution on Earth, but I also like to think of this as sort of a never-ending algorithm. I think that's a good way to frame it too. It's something that just keeps creating stuff and doesn't seem to end. You know, at least more than 1 billion years and still running is just an incredibly long time for something with an algorithmic nature to actually be continuing. And we just don't have stuff like this in our toolbox right now. There's nothing that you would want to run for 1 billion years. I mean, even if you could, it wouldn't be worth, or at least I would assert, there's nothing you can point to that it would be worth coming back 1 billion years from now to see what happened. And yet we are inside of such a system, and such a system produced us. In something like this, like here's this one run, which is one of the remarkable things about this. We're talking about one run of something. I mean, we're used to doing lots of different runs. And if you think of it sort of like a more conventional machine learning context, everything that you see in this tree could have been a separate run. Like a huge problem, like how do you build a fish? Okay, well, let's try to figure that out, and we'll run something and get a fish. But that's not what this is. This is everything was produced in the same run. And somewhere in that kind of endless saga, there's this one point, which is human level intelligence. And it's part of all of these discoveries happening in this giant tree of life. And one of the things that characterizes a run or system like this is just endless surprise. Like, it keeps on going with endless surprises, and they're all surprises. Like, none of them could be predicted. You can go back in the tree and look at the stuff there, and you're not going to be able to know from that you're going to have humans at some point in the future or anything else. So it's really about surprise and continual surprise. It's kind of the nature of this type of a system. And so the name for this that I think characterizes it the most accurately is open-ended evolution. It's evolution, but not in the sort of evolutionary algorithm sense that's more traditional, where we're trying to solve a problem, and it's more like an optimization algorithm. This is something very different from optimization. This is open-ended evolution, something that just keeps going forever and surprising you over and over again. And more generally, I would just call it open-endedness. So I prefer to drop the word evolution, although historically, the community interested in this would call itself open-ended evolution, and some still do. But the thing is that open-ended processes exist also outside of strict evolution. And for example, in the histories of aspects of our society and civilization, like art, science, technology, things like that, those are also open-ended phenomena. And they are also an ongoing cacophony of surprises, similarly to evolution. And I think it's an important observation because when you think about those things, the thing that distinguishes those things from evolution is that they are actually a product of human intelligence. And it's indicative of the fact that we ourselves have some open-endedness in our nature. It's not just that we're a product of an open-ended process, because we are, which is evolution on Earth, but we are ourselves also are open-ended in our brains, and our brains have an open-ended capacity for discovery and invention. And so learning about open-endedness is both learning about what led to us and how you create things like us, but it's also about understanding ourselves. And one of the most, I think, the most salient aspects of our nature is our sort of perpetual creativity. As you follow us over the eons, we're just amazingly creative and building in an open-ended fashion. And so what's interesting then, when you recognize this fact that open-endedness is so important to both our history and our own nature, that there's really is no algorithm, even evolutionary algorithm, that's really worth running forever, like the way you could think of Earth as running forever. And I use the word forever, I mean, a little bit in a metaphorical way, because obviously we haven't literally been running forever, but a billion years is close enough, I think, to merit the word forever. And so usually though, in the kinds of algorithms that we would run, there would be some objective function or something like a fitness or a loss or something like that. And so they would do one of two things. I mean, it would either converge, hopefully to the optimum or something really close to it, or get stuck. But from an open-ended perspective, both of these are bad. I mean, it's basically, it's over. And the whole point here is it's not supposed to ever be over. So these kinds of conventional ways of doing things clearly are not the way that open-ended systems work. And so people have reached for more imaginative ideas, like coevolution in the evolutionary literature, self-play that you see in deep learning now, GANs, A-life worlds. And there's a picture of one of those worlds. There's lots of worlds like this where creatures kind of hopefully open-endedly interact with each other. But these are known to ultimately reach diminishing returns in terms of, yeah, there's a lot of interesting stuff that you can get from a lot of these things, but eventually you're going to run out of steam, or you'll see that there's some cap on the creativity that's possible. You know, if you have GANs that have somehow absorbed face space, you've trained them on lots of faces, you're only going to get faces, right? Like, that's a problem. If you want something where it can actually step outside of the box. It's like we have a process in evolution where there were once flatworms, and eventually that led to humans. It's a completely different situation. If I had millions of flatworms, there's nowhere in there where I can infer that humans, or how to build a human sometime in the far future is possible. And so it's the same issue with most of deep learning, evolution, optimization, whatever algorithm set you're into, it's going to eventually peter out and stop producing genuinely new, interesting stuff. And so it suggests that there is something that we don't know. Because if we did know it, then we would just do it, because this would be a really amazing kind of a process to get going. Even if it didn't deliver human intelligence, it would still be quite interesting to see what it would deliver. And we just don't know yet how to do something like this. So there's something important that we need to learn here. So how will we achieve open-endedness? And I think it's a great puzzle. It's kind of a grand challenge. And so I think that the answer is that it's going to be something that involves surprises. Because if there's ever a great puzzle, something that's really, really difficult for us to solve, like it involves decades or centuries of work, there's got to be something counterintuitive under the hood, right? Because if it wasn't counterintuitive, that would mean that we would basically be able to intuit what the actual correct steps would be along the path towards it. And clearly we can't do that very easily. So there's something really counterintuitive probably lurking in the background. And I think as I've been pursuing this question of how to build an open-ended system for a long time, you could see that principle in some of my own journey in trying to understand this problem. And I've actually been interested in this for a very long time. But I didn't really have a word to put to it, I think, in the earlier years. And I mean, I was probably interested in this since at least high school, but I wouldn't have really known what to call it. But I was just interested in systems that just produce surprises and do things that are really cool that I wouldn't expect. And so, so I'm not sure when I exactly recognize that this is open-endedness is the issue that I'm really interested in. But you can see across sort of my own career that I've been at some level interested in this behind almost everything that I've done. And so I wanted to give a little bit of that breadth in this presentation. And the kind of hope that I have by showing you these steps of thinking is to give a flavor for maybe what trajectory we're on in general, or what it's like to pursue this question, and hopefully to inspire some moving beyond where we are today, and searching more forward and being open to some pretty paradoxical kinds of ideas. And so I think, like, I would start I just wanted to start here with something that's pretty old now, which is the NEAT algorithm, because it sort of reflects an early thought for me on what it would take to get to things that just continue to be interesting. And that early thought is not something that's super surprising, but at least it's important to capture it and recognize it. It's the idea that, like, things that are getting more interesting over time, well, they shouldn't be bounded. In other words, they should be able to increase in capacity, if not in complexity, at least in capacity, the capacity to express new things. And so, like in any space that you're in, if it's a finite dimensional space, eventually you're going to have to run out, right? Because it's finite dimensional. So in order to escape that space, you're going to have to go to a higher dimensional space. And NEAT was about how to do this, like, more formally in an evolutionary or neuroevolutionary system. It's basically about, can we start with really simple neural networks and allow evolution to allow those neural networks to get more complex. And it does turn out that having this algorithm around was useful for future experiments that are more close to the question of open-endedness. So this is not the end of the question. This is the beginning. You know, it's like, well, let's have something that's not bounded, but there's a lot more to it than just that. And that is reflected in some of the more recent stuff. And so I think one of the most important turning points, just for me in my own sort of trajectory of thinking, was with PickBreeder. And there actually is NEAT under the hood here. So NEAT is actually evolving the CPPNs, which is a kind of representation, which is a kind of a variant of a neural network that's going to generate these pictures. But in PickBreeder, which was a website where people were literally breeding pictures, there were actual signs of open-endedness. And this is something I want to highlight because I don't know if it's, like, widely thought of that way, or for those who actually know about PickBreeder, which some won't, and I'm going to show you anyway, so I'll fill you in. But for those who sort of know of PickBreeder a lot, will think of it as sort of a toy that was interesting, or a game maybe, where people were breeding pictures, like the way you might breed a dog or a horse. And there were humans in the loop, of course. But I think what's really interesting about it is that it really is open-ended. And I think that this is one of the few artifacts, the few artificial things that have been built that you could really say that about. So that makes it, to me, extremely fascinating as sort of a reference point for what would it be like to have an artificial open-ended complexity explosion. There's a question of why is this displaying this? I mean, I just said before, like on the last level, you don't know how to do this yet. So now here I am claiming that we did it. But the reason is because there's humans in the loop, so it's basically cheating. And if we didn't have humans in the loop, we wouldn't have a clue how to do something like this. But the thing is, that's okay. In my view, that's okay, because it's still extremely fascinating to see something like this unfolding artificially. It's like, it doesn't give us the full answer to how to build a system that's autonomous that can do something like this. But it's okay because it's piggybacking on human intelligence, which itself is open-ended. So in a sense, it's a cheat. But what it gives us is an artifact in the end, which is like the only artifact we have like this, where we know every single thing that happened in a very large, relatively large from an artificial systems perspective, open-ended process. And so we can learn a lot from it. And I think we did learn a lot from it. And that's sort of one of the things I want to point to. So the main idea here is anyone can follow up from anyone else's discovery. So like if somebody discovered this skull, then somebody else could try to breed from this skull. And so in effect, there's no unified goal for the system. And this is important, I think, for open-ended systems, is they're different from traditional type of machine learning problems where there might be some objective, like I said before. Here, there isn't any particular thing anybody is trying to or necessarily supposed to find. There's no unified objective for the system. It's true, some individual might have their own personal objective, but the system as a whole in aggregate will not have a unified objective. So there is no unified goal for the system, and that's important to get it to work. So if you were playing in this world, one of the first things you could do is you could choose to start from scratch, and you'd see something like this, which is 15 blobs. They're generated by a special kind of neural network called a CPPN. And they're going to evolve with NEAT, which means they can get bigger. The neural networks under the hood, which nobody has to know about or see or look at, but under the hood, there's these neural networks. They're getting more complex over time. And I can say which one I like. This is a very simple game, and then it'll have children. You see, I chose that one, and there's some children. There's slight variations on it. The one over here is kind of so these are basically just perturbations in the weight space, or perhaps increases in complexity in the number of connections inside of these neural networks. So the topologies could be getting more complex. And I can choose this one. It's a little bit different, right? That's a little bit different. And so then it'll have children and so on. And basically, it's just breeding is all you're doing. And so at first, if you look at this system, it looks fairly modest, maybe vaguely entertaining. I mean, if you look at the sequence so far, these are just some blobs. I'm not sure how long you'd want to play this game, because it looks like there's not going to be much more than just blobs. But in fact, that turns out not to be true. And this is kind of an important principle in open-ended systems, is modest beginnings can lead to absolutely incredible endpoints. And so you start with something like this, and you might not expect it, because look what's happening, but you get things like this in the end. And this, to me, was, I think, just incredible. That, I mean, these are from perturbing these very modest blobs from small neural networks. And so why is this incredible in my view? Is because it's really about how many iterations it takes to get these things. I mean, this is not like GANs. This is not modern neural networks. These are things that were created in dozens or at most hundreds of steps, starting from scratch, starting from just random. And that is an extremely small amount of iteration. So something very different is going on here. Like if you wanted to sort of reproduce an image here, like get a skull or a car or something like that, or a butterfly, I mean, you would need thousands and thousands of iterations at minimum, like with modern deep networks or something like that, regardless of the algorithm you're using. But these, though, are just like dozens of iterations. So something special is going on here. And clearly, we're getting enormously diverse discovery. This is just a small cross-section, of course, of all the things, the thousands of things that we're discovering. And so what is happening behind the scenes looks a little like an evolutionary phylogeny. It also looks open-ended. You know, you can see in this tree where the seed is at the top here, that every connection in this, every branch in this tree is where a single session was launched, starting from where somebody else left off. And so we don't actually see the steps along these lines. We just see the outcomes of those sessions. So these are all different user sessions, every single connection in this in this graph, in this tree. And so what you're seeing is basically the fanning out of different discoveries along completely different trajectories through the search space. And this looks like what you would expect in kind of an open-ended unfolding. But so what? I mean, this alone, like if you just look at this, it's not really like a revelation or something. I mean, it's like, okay, that's kind of what you expect when you put humans in a system like this, is they're going to be branching off of each other and looking for different things. And so what exactly is deep about this? Like, what have we actually learned that we might not have known before? And this is why I think it's useful to have an artifact like this, because you can learn things, but you have to be willing to look at it like in a lot of depth in order to sort of see what is actually going on. And we have to, be curious when we see things like this. You don't just take it for granted that you're getting things like skulls, but rather say, well, how is this happening? How could a skull have been discovered in less than 100 steps? In this search space that's like 99.999% complete garbage. How did people do this? And it turns out that there's a really, really weird answer behind the scenes here, which is that we found out that people are only finding things when they're not seeking them. I think this is a very important discovery, both for machine learning and for open-endedness in particular. And so one thing you might think is, well, how would I know that? How do I know what intention someone had, like when they were playing this game? And the reason I can know that is because I can just look at the history of every image on the site, and you see the same thing over and over and over again, which is that the thing that leads to the final product could not possibly been selected intentionally for that purpose. Like, in other words, like this egg with a hat, could not possibly, it's inconceivable that this was created with the express purpose in mind eventually of getting a teapot. That's impossible. It's not possible that the person who found this dish was thinking, this is what we need to get to skulls. Or we needed the letter G, it looks like a G, to get to the planet Jupiter. Or an alien face to get to a car. Like, all of these things are inconceivable as intentional acts. Rather, it was that they weren't looking for the final products, and that's why they found those things. So if you were looking for something like a teapot or a skull, you wouldn't get one, because you wouldn't select an egg with a hat if you're looking for a teapot. And so there's this really counterintuitive, paradoxical moral here, which is you can only find things by not looking for them on PickBreeder. And I think that this principle, this is a very general principle. So it's not just about PickBreeder. That's why it's so fundamental and important. And it probably gets to the level of controversial, because it would be more comforting to believe it is only about PickBreeder. It's like there's something special about PickBreeder. But if you really think about it, why would this only be a principle in PickBreeder? It's a general principle of discovery of really, really, really hard to find things. That a lot of the time you can only find those things by not explicitly looking for them. Now, I mean, why would this be? Why would this be in PickBreeder or in general? And it's a simple explanation. It's because of what's called deception, which is that the actual route that leads to something interesting often doesn't resemble that thing at all with respect to any metric that any sensible person might formulate. Like, it's not clear at all that a donut here at the 20th iteration of this process leads to a skull like 50 iterations later. This is completely mind-blowing. Nobody would ever predict this. And yet this is the case. And it's no more clear that a flatworm leads to Shakespeare. You know, you don't get Shakespeare from any other path in the entire tree of life over more than a billion years, other than going through a flatworm. And there's no way anybody could predict something like that. And so the problem here is that if you wanted a skull, you would never select a donut. And so it's very hard to get to these things if you're actually trying to get to them. But rather, you would select a donut if you don't care about getting to a skull. And there the paradox arises. And sometimes I call this the objective paradox. And I think that this paradox is very important. So the paradox basically is, if you have an objective, you stop yourself from achieving it. And the only way that you could achieve it is by dropping the objective. So it's very counterintuitive. And so this is a very important paradox and principle, because it's recognizing something about why open-ended systems are so powerful. It is not to say that you can always get what you want. That would be a crazy suggestion. Like, drop your objectives and then you'll just get whatever you want in life. I mean, obviously there's no guarantee. It's a more nuanced and a more subtle insight that's even perhaps more disturbing, which is that it is important in order for us to find really hard to find things, to drop our objectives and just search in an open-ended way, but we don't know what we're going to find. So that's a very kind of a strange thought, but it's something we have to grapple with if we're interested in open-ended systems, because it's sort of fundamental at the core. Is that the point is, it's not that we can control where we're getting to, but there are places that we will never get to if we don't do this. And so this was to me, like, this is a revelation to me, coming out of PickBreeder, that I noticed with my colleagues who worked on PickBreeder with me, and was just kind of blown away thinking about it, and eventually led to the novelty search algorithm that I did with Joe Lehman, which is inspired directly from these insights in PickBreeder. It's like, well, if this is the way that a lot of really interesting things are found, then let's try to really formalize this into an algorithm that respects this idea, which is like, let's make an algorithm that doesn't try to actually solve a problem. It doesn't have an objective, but it just tries to do new stuff all the time. And this leads to the idea of divergent search algorithms, or search algorithms that don't actually converge towards a point intentionally, by design. And it's a weird idea at first when you see something like this, because you you will, if you see something like this, you will initially have the intuition that it will be just crazy and not do anything useful. And this is a wrong intuition, and a very important intuition to get out of, because most people equate something like this with randomness. It's like, well, it's not trying to do something, it's just trying to do something different, but that's just totally random. So why would this do anything? But you have to think back to PickBreeder and think, is that doing something is that not doing something interesting? It's not trying to do anything in particular, but it's doing something very interesting. But why would things like this do something interesting? So why would evolution on Earth do something interesting? It's not trying to do anything in particular. And I think PickBreeder helps us to see, which is why it's so useful to have these kind of artificial systems, artifact to look at, intuitively why this isn't just random and expected to do something crazy. And the reason is because I would really think of these kinds of systems as information accumulators. Like, so if you think about doing something new or interesting, now novelty search is about doing something new because there's the word novelty, but that's really just, for me, it's just a proxy for interestingness. Really what we want is something that just drives towards anything interesting, but we don't care what it is. And we don't know how to formalize interestingness. So here it's kind of a proxy or something that's close enough to at least work somewhat, is novelty. And why would novelty be an information accumulator? Well, the thing is that in any system which has some kind of rules, like say the universe, it has some laws, right? Like you can keep on trying to do something new, but if you do that, eventually you're going to have to learn to do something or learn something about the universe itself. In other words, like imagine you're locked in a room and you're trying to do something new over and over and over again. Well, let's not say you're locked, you're in a room. You're in a room and you're trying to do something new over and over and over again. So you can bounce off the walls, you can jump up and down, you can do somersaults, you can do anything you want. And for a while, you're going to be successful, right? You're going to be successful at doing stuff just by flailing around randomly. But then something is going to happen where there's nothing else to do because you're in one room and there's nothing else to do. And so there's something you're going to have to do, which is leave the room. Now that's a big problem because you're going to have to figure out how to get to the door, how to recognize the door, how to open the door, and so forth. And so suddenly you have to actually start understanding the universe around you in order to do something new in it. And that means you're accumulating information. So basically by moving towards novelty, you're forced to accumulate information. And in this way, I think you can look almost at something like the phylogeny of life as almost like an encyclopedia of what's possible in the universe. It's kind of an interesting way to think about it. Like, you know, there are things we can do. There are things we can do that are affordances that are possible. Like we can respond to photons and that sort of seeing, and we can respond to vibrations in the air, and that's because there are vibrations in the air, and that's called hearing. And then we can do various physical things to respond to utilize friction or counteract gravity and so forth. And so like all of the different things, I mean, sonar, for example, that the organisms of the world do reflect sort of the properties of the universe around us in a way. And in fact, like, you know, sending a spaceship to the moon or to Mars reflects that information has been encoded now at such an extreme level about like the actual structure of the universe around us, as like what the planets are in the solar system and how to actually get to them. And so information accumulation is what you expect, and you don't expect it to end, which is one of the power of open-ended processes. And so that is why we see results like the one here on the bottom, where you just play a video and hope it works over the internet, where if you ask this biped walker just to do new stuff without actually asking it to get better at walking, that's the novelty search view on the right, versus actually try to reward it for walking farther, you get walkers that are better from the novelty search perspective. And this is not always the case, because like I said, there's no guarantee of solving something if you're just searching for pure novelty. But it's sometimes the case. And the reason is, like, it's always counterintuitive at first, and it seems weird. It's like, well, how could it be that it would get better when it doesn't know what it's doing? And the answer is that, well, it goes back to these intuitions. Like, well, the thing is, deception is there. It's not necessarily the case that the things to lead to walking look like walking. And so when you're in a space like that, you can get a better version of walking from not actually trying explicitly to walk or to walk farther. And this is actually what we see as a phenomenon. So it's very interesting to start to see this stuff. And so this is not the end of the story in open-endedness, it's just the beginning. And so, but it's starting to give us some insights. We're starting to encode some of these ideas into algorithms. And one of the insights I think this encodes is the idea of stepping stone collectors. I think this is very important for understanding open-ended processes. Like an open-ended process is something that collects stepping stones. And it's something that would store them in kind of a growing archive. So that the point is that these stepping stones become potential stepping stones to more discoveries, which generate more stepping stones. So the more stepping stones you have, the more places you can get. So like a stepping stone collector is something that gains power over time. It's a really cool aspect of these kinds of systems like PickBreeder and novelty searcher stepping stone collectors. And the longer you run them, the more powerful they are. And this is not necessarily the case like in most machine learning systems. But like if you came to PickBreeder 2 years after it was created, it's a way, way more interesting system than the day it was created. Because there's more stepping stones, so there's more places you can get. You know, the first time someone discovers a face, suddenly face spaces open up and PickBreeder suddenly becomes a face breeder. It wasn't that the day before. And so nature is also like that. Like the longer nature has run, the more possible amazing things can come out of it. And so this is a really cool property, which is clearly dovetails with open-endedness. And so novelty search led eventually to what are now being called quality diversity algorithms. And so people recognized, and it's not hard to see, it's sort of inconvenient that in novelty search you can't say anything about what you like. Like it's a bit of a straitjacket to not be able to tell the algorithm, I like this kind of thing, I don't like that kind of thing. Sort of the kind of thing we would call an objective. But the problem is we're sort of disavowing objectives, like they're antithetical to an open-ended process. So this is a very delicate balancing act to combine a notion of quality with a notion of diversity or novelty. And so it sort of spawned a new field, which we call quality diversity, and the quality is sort of the objective style of thinking, and the diversity is this novelty style of thinking, or the open-ended style of thinking, and figure out how to mesh these two things together, which is a very delicate thing, because it turns out that if you don't do it in an intelligent way, the objective version of the view of the world will completely overwhelm the much more delicate divergent view. So you have to do this carefully. And some algorithms like novelty search with local competition and map-elites, and map-elites, which is a very elegant open-ended algorithm, or at least a quality diversity algorithm moving on the road towards open-endedness, were started to come out that sort of very carefully slipped in a notion of quality into these overall non-objective processes or divergent processes. And the kind of thought in these algorithms is, let's find the best possible representative of diverse niches, which we've sort of started to call a repertoire. Like, what is an algorithm that can generate a repertoire? Lots of different abilities, as opposed to just solve one problem, solve lots of problems in a single run. So we're back to that theme of like the single run with lots of interesting solutions, just like sort of the tree of life in nature, where you've got things like, you know, photosynthesis and human brains in the same run. And so when we see like on the cover of Nature, something from map-elites, where they ran this quality diversity algorithm to get a whole giant repertoire of walking gaits. And then they said, look, this is actually useful. If you have this repertoire, there's many, many different ways of walking. And if something happens to the robot, like if one of its legs breaks, we can then go and find which part of our repertoire has a gait that might work for the robot in its new unfortunate state. And so sort of to say that this is why it's useful sometimes to have repertoires, or like repertoires here of diverse kind of creature morphologies and their respective walking algorithms. In this other paper on the NSLC method. And so these quality diversity methods are starting to move in a direction which is looking a little bit reminiscent of what we mean by open-endedness. And in fact, quality diversity now is a growing field. And Antoine Colley maintains this, I think, really nice archive. So if you're interested in this field of quality diversity algorithms, and it's obviously growing pretty fast. And so it sounds like, you know, maybe I'm almost declaring victory or something, but I really am not. I really think we shouldn't do things like that, like declare victory. Rather, what I think we should be is extremely self-critical here. You know, you cannot celebrate too prematurely on the topic of open-endedness. And just like sort of AI, I mean, it's a grand challenge on the same scale. Because look, I mean, like open-endedness in its full bloom is basically the power of creation. I mean, we're talking about something that created all of living nature. Like, it's biblical in its power. And it's literally that powerful. And so, like, to look at a little fun little system that generates some variance of something and be like, we figured out open-endedness, would be incredibly naive. Rather, I think we need to be very, very critical and sort of always looking at what is missing in our systems that's preventing them from going for 1 billion years. Because I think it's clear that these quality diversity algorithms are not worth running for 1 billion years. Far, far from it. But why? I mean, that's an important question if we're really going to get to open-endedness. What is missing now? Well, think about it. What happens when the space impossible is filled? Like, you have this robot, like, you find all kinds of gates. Well, at some point, you're going to fill up all the possibilities, right? There's not going to be something new to do. There's nothing new left to do. What causes new possibilities to arise in the world? and basically forever. And there is an answer to this question, and quality diversity does not address this answer. But the answer is that the system needs to generate both new opportunities and search through them at the same time. Quality diversity's got this idea of search through down. They've got that idea down. But the thing is, where are the new opportunities coming from? They aren't coming from anywhere because there aren't any new opportunities. The space of the possible is fixed from the beginning. We're just going to plunder it and then it's over. And it's not like that on Earth. And so on Earth, and I like to use the example of giraffes and trees, you've got new opportunities and new solutions coming in all the time. It's the new opportunities that give it this amazing capability to go on forever. So in other words, like a giraffe and a tree are both actually points in a space of possible solutions to the problems of life, you could think of it as. Or you can think of them points in a repertoire of different ways of solving this problem. But they're not just that. They also are new opportunities because look, the tree itself, not only is it a solution to a problem of getting nutrients out of the ground, but it also presents an opportunity for the giraffe to find a new way to actually live in this world. And without the tree, we wouldn't have the opportunity to have the giraffe. And so the things that are being generated on Earth are both solutions to problems and opportunities to solve new problems. And that's why it can keep on going in an open-ended fashion. So it's very important to have both sides of this equation being filled by a true open-ended algorithm. And so in my research and with my colleagues, we started to turn to trying to answer questions about how systems could do both of these things at the same time, both generate opportunities and solutions to them in the same run, sort of indefinitely. And that's where this minimal criterion coevolution algorithm comes in. This is one example of such an attempt. But I also wanted to call out that before this, and I didn't focus on this here because it's less of a machine learning and more of an A-life thing, but really this is inspired from the Chromaria artificial life system, where a lot of these principles were first really laid out that I did with Lisa Soares, because I know Lisa is here. And so I just wanted to highlight that a lot of these ideas come from actually doing as artificial lifestyle experiments. And here we actually tried to formalize them into an algorithm called minimal criterion coevolution. So I just want to give a glimpse of this, or sort of saying now we're moving out of the conventional QD towards things that also generate new opportunities. So one of the simplest way to think about generating new opportunities is just to think of it as sort of two populations of things. There's solvers solving problems, and then there's problems being generated. And so think of it for simplicity of mazes, and then neural networks that drive robots through those mazes. And that's the example that we used in this line of research with the MCC algorithm, or minimal criterion coevolution. And so here the idea, so it's just let's just generate mazes and generate solvers for mazes. And so yeah, this is not exactly analogous to what's going on Earth. We don't have these strict two concepts. In fact, in Earth, the two concepts are sort of interchangeable. Like I pointed out, a tree is also a solution. It's not like a maze where it's only a problem. It's also a solution to something. But we also, I think, are totally willing in machine learning to diverge away from a strict reproduction of what's going on in nature. That's not our point here. We're not computational biologists. We're doing AI research, right? And in AI, all we care about is abstraction. We want to find the essential principle and then abstract from it to get the actual algorithmic thing that's going to work for us and do what we want it to do. So this is an attempt to do this at a very abstract level. And so the idea here is, okay, we've got the mazes and we've got the solvers, and we can self-generate the opportunities, or the mazes. And it's sort of a two-population coevolutionary thing. But what we really were trying to do here is to distill a theory down to its essence. So I like to do that sometimes. I like to say, what is the most essential insight to get us to a kind of phenomena that we're interested in. Eventually we might want to elaborate, put some bells and whistles, but I'm thinking what's the absolute simplest possible insight here? And the insight here is almost forget optimization even, just let drift do the search. Just drift through a space with almost no selection. There'll be some selection, but almost none, not in the conventional sense. And just rely on the idea of divergence. The divergence alone will cause us to pass through an unending space of problems and solutions. And so this relies on a principle which is sort of more obscure in machine learning because it's not very much discussed, called an MC, or a minimal criterion. And the idea is that these solvers in these mazes are going to be drifting through mutation through their respective spaces, but they're only going to be allowed to reproduce if they fulfill a minimal criterion. And the minimal criterion is that for a maze, it has to be solved by somebody, and for a solver, it has to solve a maze. But if they do pass that minimal criterion, then they get to reproduce guaranteed. So this is a very strange algorithm. This is not like a normal evolutionary algorithm, because there's no gradient following here, and there's no continuum of fitness. There's no comparisons going on. If you pass the minimal criterion, you're guaranteed to continue. And it's inspired kind of by this observation in nature that, you know, if you reproduce, that's kind of the minimal criterion of life. Like, as long as you're a walking Xerox machine that can make a copy of yourself, and you do that, then your lineage will continue. And so this notion of minimal criterion is sort of an abstraction of thinking about nature and about open-ended systems, where it's like, well, as long as something passes this test, let's see what can happen. Let's move forward in that particular trajectory, and many others where it's the same, and be completely agnostic with respect to anything being better than anything else. In fact, we're getting rid of the idea that some things are better than others. Let's just see everything that passes through this minimal criterion. And so I'm going to skip through this algorithm description because I gave you the basics enough to understand it, other than just to say that we did find we had to do one other thing, which was actually a little bit aggravating to me, which is we had to add speciation. Like, it would have been nice if the thing I just told you on the previous slide, just on its own, did everything we wanted. We got huge diversities of increasingly complex mazes and maze solvers. That would be really cool. But it turned out we couldn't do that. It would be somewhat converged unless we introduced speciation, which is like an enforced diversity pressure. We used neat style speciation here, like from the neat algorithm. But it just, to me, that was like an extrinsic addition that was kind of unsatisfying. Because obviously very artificial, like we're enforcing this thing in an artificial way. And it would be nice if it just organically emerged on its own. It would actually keep increasing in complexity without it, but it would be like along only a single trajectory. Like, all the mazes would be really similar during any given iteration. They would get more complex over time, but they wouldn't diversify like the way you hope to have this big phylogeny. Now here, you can see that like it actually did work. Once you put the speciation in, we would get increasingly complex mazes and neural networks that could drive a robot through them basically indefinitely. So there's some hint here of what we want. Like, this might be worth coming back 10 years later. I mean, it might be like, if you came back enough years later, assuming you had enough memory and time, you might have a maze as large as the galaxy. Like, it's totally possible, and a neural network that would solve it. And there's basically no other way to get stuff like that. Like, it's ridiculously big. Now, I agree with people who might be thinking, but why would you want that? Yeah, that's a little bit of a problem here, is that like, unless you're interested in mazes and maze solvers, it's not like you really necessarily care. So there's still something that seems to be a little bit slipping through the fingers here. Like, we don't completely have our fingers on, well, how do we get things that are just like really, really diverse? Like, not just diverse mazes, but like anything you can imagine diverse. And that's not really happening here. But still, we're getting a hint of what we want, aren't we? Because of the fact that like, this actually doesn't seem to ever end. Things just kept on getting bigger and bigger and bigger. And so one thing we did, though, that I think was really interesting was to get rid of speciation very recently. This was from this year. And we did find a way to do this organically, which was we created a resource limitation. We said, like, a maze can only be used by a finite number of maze solvers in order to satisfy their minimal criterion. So you can see how this could push you towards diversity, because like, if a maze gets used up basically by a current number of maze solvers in the population, then other maze solvers have to use another maze that's different. And then so implicitly it might push towards diversity. And it turned out it did. It was really great. It was actually much better than speciation. Like, these graphs are showing like that there was more deceptive junctures in the mazes over time generated, and much bigger distribution of maze sizes, and every measure you look at was better than doing this kind of artificial speciation that we used to do. And so what I think is interesting about this is an extremely simple algorithm. Like, it's like basically just says, everybody tries to produce an offspring, and if they pass the minimal criterion, then they get to reproduce. And the only restriction is that, like, if a maze has already exhausted the number of maze solvers that can solve it, then it can no longer be used. and you know, it relates to resource limitations in nature and things like that. Like that's also a driver for speciation in nature, and that's the whole algorithm. Like there's no like fitness comparisons or taking the top end of the population or anything. We just throw things away if they age out. So it's not based on fitness. It gets old, we just throw it away eventually. That's how we keep things finite. And yet it works, and it works better, in fact, much better. So I think that's really interesting. And it's kind of contrast with this one other angle that we took, which is like not going for simplicity, but going for power. And that's how I would characterize the POET algorithm, which I recently did with some colleagues when I was at Uber AI Labs. And this is related to a whole host of algorithms. Like it does have some connections you can draw to the MCC, but also novelty search and some other algorithms like the CMO algorithm, Mapolites. It's just like borrowing a lot of ideas from all kinds of things. But basically the idea is like we have the pairing concept, like that they're going to be domains so we can get new opportunities. But also we're going to have this idea of optimization back in, because optimization is powerful. I mean, like reinforcement learning in deep learning is powerful, and we don't necessarily want to drop all the powerful things in what might be like the final open-ended algorithm. Not to say that this is it, but it's something that we want to be able to incorporate. And MCC doesn't have that because MCC is really going for extreme simplicity. And so in POET, the idea is like, let's optimize constantly in many, many diverse environments all at the same time, and sometimes transfer between those solutions. So take a solution from one and try it in another. And hopefully in doing that, we get these circuitous pathways, like the deceptive pathways can be covered through the stepping stones of environments that are going to be generated here. And our hypothesis is this is the only way that some solutions could ever be found. So the idea is you've got an agent, and in this case, we're going to look at biped walkers in these 2D obstacle courses. And this is called like the hardcore biped. It's in the Box 2D, in the Box 2D game engine for anyone who's interested. It's easy, you can download it and get it yourself. And so we said, let's try to get this thing to go through innumerable diverse obstacle courses. And we think of it as a pairing of an environment with an agent. So one obstacle course with the agent trying to solve it. And the idea in POET, which is called the paired open-ended trailblazer, because we're doing these pairings, is that like for every environment agent pair, we're going to hopefully generate new environment agent pairings from that and new from those. And so we're going to have a divergent process. And when we generate something new, like it's basically going to be that we're going to mutate the environment to get a new environment, and then we're going to take its paired agent and move it up to that new environment. And hopefully it'll still have some ability in the paired environment, but we'll continue optimization through whatever RL algorithm we're using. So we're constantly optimizing in all these environments. But the really interesting, cool part of these dotted lines, like these dotted lines means we're going to try agent 0 from environment 0 in environment 2 to see maybe it's actually better because of serendipity, because of deception, because often solving a problem that doesn't seem related to the problem you're trying to solve is actually better than trying to solve that problem. And so this kind of goal switching is the term we use for it, is really important to making this algorithm so powerful. And then hopefully we just get more and more environments and agents, and it just keeps going again, hopefully forever. And so we see that what we do here is we reproduce environments and carry their agents along with them. I'm not giving all the details, but we also filter by minimal criteria here on our environments, and we rank them by novelty. So again, we have a diversity pressure. So you can see that diversity is very important in these algorithms. Like, don't forget it, because what we found is like without it, they do tend to kind of go on a one track. Like they might get increasingly complex, but you don't get the divergent like tree of life kind of phenomenon. And so hopefully we just keep on adding more and more stuff, like you get a bigger and bigger pool. And we want to see divergence and increasing complexity. And in fact, our initial results in this environment here did have that. We used a direct encoding of the environment. And we found, importantly, that there wasn't any other way to actually solve the environments that were generated. This is actually a picture of the encoding. Like there was stump height, gap width, step height. So we're basically searching in this space for environments. But if you tried to like do direct optimization, like with the same optimization algorithm which we used happen to be ES, or the evolutionary strategy algorithm, in any environment generated, it wouldn't work. And even a curriculum we tried auto-generating curricula, that wouldn't work. So like it goes back to this objective paradox again. The only way to solve these problems is by not trying to solve them. And this again was coming up now in POET. this is evidence that the goal switching matters. Like we saw that like in the full poet runs, we would find these extremely challenging environments over the course of the whole run. That's what this graph shows in the green part here. But if you take out the transfer and you don't do the goal switching, it finds 0 of the extremely challenging environments. So clearly it's critical to have goal switching to be able to find these types of things. But the environment space is limited. And I know I'm getting a little over time here, so I'm gonna try to wrap up in a minute. Sorry about that. But I think this is an important point because it's another kind of angle on open-endedness, which I think is not satisfyingly closed right now, which might be some of the discussion we might have, is that, look, the environment's also extremely important. We have to recognize that, and a lot of people do, that like it's not just the algorithm. Like this is a cool algorithm, but the problem is here, like the environment itself is limited. You're gonna run out of things to do. So we tried to make a more rich environment, but I want to acknowledge that even as we did that, there's still a huge question on making environments where the possibilities are unbounded. Like that's still an open question. And we need to think about that. And this doesn't necessarily address that, but it does show that if you improve the environment, you get better end results. So the environment matters a lot. And so we started using a CPPN-based encoding, like the kind of thing that was in PickBreeder, instead of this like really simplistic direct encoding that we had before with things like stump height. So the CPPN can express any terrain pattern you can ever conceive, basically, because it's like this network that can express any 1D function, because these are basically 1D functions in space. And so we can get all kinds of more diversity than we could before, but the thing is we lost our novelty measure, because our novelty measure was based on the encoding that we had. And so that's another, it points out another thing is we want diversity pressures that are independent of the specifics of the environment that we have, so that we can have domain independent algorithms. And so we had to come up with a new domain independent measure of novelty in order to get the diversity. And I think it was kind of clever. It was basically, we called it the performance of all transferred agents environment characterization, or the PATA EC. And basically what we said is like, if you rank all the agents, all the current paired agents in a given environment, you'll get a certain ranking. But if you have a genuinely new environment, that ranking should change. Like here's a new environment. So like, look, this guy used to take really high steps. That wasn't really great for this environment. But if you look at him in this environment, then the stuff that this agent is doing actually might be better for this one. So the ranking of agents in this environment would be different. And so if the ranking changes, we interpret that as a sign of novelty, like this environment must be new. And so we can actually, and that's a domain independent insight. It doesn't matter what the domain is. If it changes the rankings on your current solutions, it's probably something novel. And it turned out that that actually worked well for enforcing diversity. So we got a domain independent measure, which is exciting because now you can apply this enhanced poet to any domain. And you can see that the diversity just visually is obviously way more in what you get in these CPPN encoded things. And here you can see, hopefully, if it works over the internet, these vast diversity of different kinds of gates and solutions for all of these crazy types of situations that Poet was able to generate and solve. And then again, we found that like you can't solve these in other ways. Like we tried with ES, we also tried with PPO in this case. We tried a different RL algorithm. Because the truth is the inner loop, it doesn't matter what the RL algorithm is, and it doesn't matter if it's evolutionary. And I don't want to convey any connotation that everything has to be evolution. It doesn't. Evolution is not the intrinsic thing here that makes things open-ended. It's the idea of having a population-based system that's collecting stepping stones, which we can express through all kinds of different algorithms. And so here we just said, okay, well, let's try with PPO and the ES to like overcome this inner loop and say, can we just optimize towards some of these environments without Poet? And again, it was dismal. Like if you look at like the solution rates, like at the late stage environments, it was basically near zero, even with a curriculum. So on the right, we see with a curriculum, we developed a curriculum algorithm, didn't help at all. Poet can solve these environments and generates environments that it can solve, but these other reinforcement learning algorithms are dead on arrival. And it just generates, again, this issue of you have to be able, you can only solve some things by not trying to solve them. We also found innovation lasts much longer. This is a graph of the original Poet and the enhanced Poet. And you can see the enhanced one just keeps innovating. And we had to invent a new measure, and I won't tell you the details of that measure here for time, but we had to invent a new measure to actually measure open-ended progress. This is another element of our field that we have to work on, is how do we objectively know that we're succeeding when we have no particular objective in mind. And so we're starting to make a little bit of progress and be able to measure, and you can see it did distinguish the old Poet from the new one to show that it actually does innovate for much longer. So I'll end on just sort of summarizing where we are today and answering a couple questions that some of the organizers put to me that I think are interesting. So I just want to point out we are starting to understand some things about how to trigger open-ended processes, like minimal criteria, generating new opportunities, transfer and goal switching, the need for diversity enforcement. Like these are actually useful principles we're starting to. So I think we're making actual progress in this field. Also, that environments are extremely important, and I think are kind of getting the short end of the stick so far. We need to have way more discussions about environments. The algorithms are getting really good, but if we want these things to continue on forever, like it's clear we're gonna have to address the problem that environments are limited, and we don't really understand why. It's like a whole other field even. It's not like the normal intuitions of machine learning, like what makes environments unbounded in their capacity. It's just an extremely fascinating question that hasn't gotten enough, I think, focus yet. Now, looking at some of the interests of some of the people here at the workshop today, can we extend open-ended algorithms to a multi-agent formulation? I think it's clear that there's a multi-agent angle on open-endedness. Like, think about the giraffes and the trees. They're both effectively agents in the world, right? And somehow it's through their interaction that we're getting an open-ended process. And so, like, you can call that like the intelligence or interaction view. Like, it's an A-life world kind of a view. Like, if lots of agents can interact with lots of agents through any kind of conceivable thing, it could be a coevolutionary algorithm, self-play, A-life world. But that somehow seems very useful, like because of our interactions with each other, the richness of each other allows us to have all kinds of different interactions. And so clearly that's possible. There's more exotic things, like I was looking at the Badger architecture from some of you from Good AI. And you know, like when you think about things like experts and specialists, you could imagine something that generates all these specializations like Poet does. Like basically it's generating a bunch of specialists for different environments and somehow aggregating them later into some agglomeration of experts. Obviously, you'd have to be careful about how to do that. What do you do to do that? But could it turn into something like, I should have put in quotes, a full Badger, because there's nothing like Badger architecture exactly. There's all kinds of details I'm glazing over. But something like that could be interesting, that the repertoire, in other words, the repertoire could be eventually combined into something new. And finally, on the point of meta learning, could that be applied on the inner loop? I mean, I think that clearly it can. I mean, actually, it's an inner loop in some cases, because if you think about it, Poet has an outer loop of environment generation, an inner loop of environment optimization, and then there's even an inner loop, which is the individual trying to solve the problem in the environment. Now, right now, it's just a static neural network, but it could have been something that was plastic on the inner loop, and it could have been actually had to learn in order to solve that problem, but that's not needed in those terrain problems. So I think it's partly a question of the environment. Like, does the environment have sufficient complexity where learning actually would be useful on that inner loop or inner loop, depending what algorithm you have? And clearly it is, like in human life. Like we couldn't exist without learning in the world that we find ourselves in. But sometimes it's challenging to formulate worlds where it would be essential. So it's sort of a question: would it be advantageous to actually have that learning so that meta learning actually comes into play? And so all of this could be on the path to here. I want to just tie it back to why we care about this from an AI perspective. This is where we hope to get. It may be that these are the types of algorithms we need to get there. So thank you. And please feel free to email me. Either email would work. Great to have this chance to talk to you today.
Thank you very much, Ken.